So today we're going to be doing two different examples. One simple but life-changing, the other one not so simple and hopefully just as life-changing. So we'll go with the simple one first. So here it is. So I have a flow and it is being turned, but instead of doing it like we've been doing it, where it's just one expansion, this time it's doing it twice. So I have it right here. I have, let's say, a 15-degree angle right here. And then I'm going to say, you know what, another 15 degrees. We'll make it equal. No reason not to. And so I have a flow coming in. We're going to say that this is Mach equals to, I'm going to just say 2.0 to start. And I want to figure out what is my Mach number when I get down here. What is M3? Now, we know how we solve these problems. And so I'm going to do it how I expect you would think to do it first. Your first thought is, well, I'm going to ignore this guy down here in the end. Like, I'm not going to care about this one yet. I'm going to focus in on this one. So let's figure out what M2 is. There's going to be an expansion fan right here. We'll draw it. There'll be another expansion fan right here. Cool. So I'll find M2, and then from M2, I'll find M3. It makes sense. That's a good way to go about it. And as a note, for this problem, I am going to go to the closest value in the tables. I'm not going to be interpolating because I'm trying to teach you a concept here. I'm not really too worried about getting the exact right number there at the end. So for any of these expansion fan problems, we're always going from a Mach number to a Prandtl-Meyer function. We then add our deflection angle, and then we go to get V2. And then we go back to find our second Mach number. So that's the basic process here. And you can kind of guess that if we're doing it this way, I can say, okay, M2 is going to be, think of me, deflection angle 2. And I can add my second deflection angle, get V3, and then back to M3. So, like, I've got a good process there. We've done it a bunch before. So let's go ahead and do that. So my first Mach number is 2.0. I'm going to jump to the tables. These are in your book. We'll look for Mach number of 2. And my Prandtl-Meyer function is on the third column, not the second. Or sorry, second column. Ooh, good thing I checked. Not the third. There we go, second column. So I get Mach 2. I have 26.38 degrees. Okay, so I see that right there. I'm going to go ahead and plug it in. So V1 is equal to 26.38. My first deflection angle is 15 degrees, which means that V2 is going to be 41.38 degrees. Not bad. And so I now go back to the tables. Like, we're going to be jumping back to the tables here. And once again, I'm going to skip on the interpolation. I'm just going to find the closest value just for simplicity's sake. You would need to interpolate if you wanted to get a truly accurate example. So I see that lower values are up, higher values are down. So I'm going to scroll down a bit. And oh, that's pretty dang close. 41.41 degrees, which is a Mach number of 2.6. Okay, so 2.6 is my Mach number for M2. I love these tables. They're super easy to work with. They don't make it really hard on you. So I now know what that is. So my Mach number right here, that's equal to 2.6. And so I continue this process. Mach number 2, well, this is going to be the same exact value. And what is my second deflection angle? Well, I can pretty much forget that this part exists now. And if I were to redraw it with my flow being horizontal, it would look just like this again. So my flow right here, this is M2 now. It's equal to 2.6. I have another deflection angle that's equal to 15 degrees. So it's just 15 degrees. It's really, really easy. How far is my flow being turned? That's all I have to figure out. How far is it being turned? And I forgot to draw my expansion fan. There you go, pretty picture. Happy days. So I know what my deflection angle is. It's just 15 degrees. It could have been anything else. And so I'm going to add it on to this. So theta 2 is equal to 15 degrees. That means that V3, our Prandtl-Meyer function at the third one, is going to be equal to 56.38 degrees. Okay, so I know that. Now I get to go and find out what my Mach number 3 is going to be. Let's see. So once again, I'm going to scroll down here. I'm getting faster and faster. And I'm going to just say right here, 56.07, that's close enough. I should probably interpolate because it's like halfway in between. And so that gives me like 3.35. 3.35. So my Mach number would then be around 3.35. But here's the thing that I hope you noticed based on how I wrote it out. You notice something right here, that this right here is kind of redundant? Like, I did the same step twice. Like, why did I do this twice? I used my Poynting-Meyer function to find M2, and I used M2 to find the same Poynting-Meyer function. I already knew what it was. Like, why did I have to go back to the tables? The answer is I didn't. If I don't care about my Mach number in between, like if I don't need to know that, all I need to care about is the deflection angle. So if I was going to do this again, going just straight from M1 to M3, I might write it like this. So M1 goes to new 1, and then I'm going to add all of my deflection angles. So plus deflection 1, plus deflection 2. I could have like 15 of these so long as there's no shock waves in between. And I can keep on going all the way down the line, and that will finally give me V3. And then I go back, and I'll get the exact same value. So if I looked at this again, I would have, this is equal to 26.38. I would then add 15, and add 15 again, to get that this is equal to 56.38. I don't have to do that intermediate step. If I don't care about the information in between, I get to ignore it with the Poynting-Meyer function. And it's the same with the properties. I don't have to know what happens in between to find the properties from the beginning to the end. Because this is isentropic, I can just look at the final value for the Mach number and the initial value and get all the properties and how they have changed from one section to the other. So this is a pretty simple example, but I want you to realize that it's wonderful because it doesn't really matter how I have it set up. If I change it like, 4 times or 2 times or 8 times, or even if I keep on going all the way around, you're like, when does that happen? Wind tunnels actually do this, where they turn the flow all the way around. I can use that information to figure out how fast it's going to be going. So, thank you for listening. I hope this helped you, and I'll see you next time.